Hello everyone. In this lecture, we are going to solve problems on Z transform using definition of the Z transform. In the examples, find Z transform and the region of convergence for the following sequences. In that, first sequence is whose general term is f of n is equal to 3 raised to n for n greater equal 0. In the solution, first of all, using the definition of Z transform, we will be getting Z transform of f of n is equal to summation n equal to 0 to infinity 3 raised to n into Z raised to minus n. Put values of n one by one. So that will give us 3 raised to 0 Z raised to 0 plus 3 raised to 1 Z raised to minus 1 plus 3 square Z raised to minus 2 plus so on. We will rewrite this term and we will be getting it as 1 plus 3 upon z plus 3 square upon z square plus so on, which is in geometric progression with common ratio 3 upon z and the first term is 1. Therefore, infinite sum will be given by first term, that is 1, divided by 1 minus common ratio, which is 3 upon z. And it is true for mod of 3 upon z, that is the modulus of common ratio strictly less than 1. Simplify the expression, we will be getting it as f of z equal to z divided by z minus 3 for mod z greater than 3. So which is the required z transform, and its region of convergence is mod of z strictly greater than 3. So which is the circle with center at origin and radius equal to 3. And the region of convergence is the region outside of the circle. Now, next example is in which general term of the sequence is f of n is equal to 1 upon 6 raised to n for n strictly less than 0. Solution. By definition of Z transform, we will be getting, so as we have been given n strictly less than 0, so in the definition of Z transform, we will consider the summation where n runs from minus infinity to minus 1. So n is taking negative values only. 1 by 6 raised to n, Z raised to minus n. Rewriting right hand side, we will be getting summation n equal to minus infinity to minus 1 6z bracket raised to minus n. Now replacing the values of n one by one starting from minus 1 biggest number, that will give us the expression 6z raised to minus of minus 1 plus 6z raised to minus of minus 2 plus 6z raised to minus of minus 3 plus so on. Simplify this expression, it will give us 6z plus 6z whole bracket square plus 6z whole bracket cube plus so on. Again, which is in geometric progression with common ratio 6z and the first term 6z. Therefore, the infinite sum will be given by first term divided by 1 minus common ratio, that is 6z. So we will be getting 6z divided by 1 minus 6z, and which is true for the modulus of common ratio strictly less than 1, that is mod of 6z strictly less than 1. Simplifying the region of convergence, we will be getting it as Z transform of the given function is f of z is equal to 6z upon 1 minus 6z for mod z strictly less than 1 by 6. So which is the required region of convergence. So it is the circle with center at origin and radius equal to 1 by 6, and the region of convergence is portion of the circle inside the arc of the circle. Next example is the sequence whose general term is f of n is equal to 1 by 5 raised to mod n for all n. Solution. Using definition of Z transform, we will be getting Z transform of f of n is equal to summation n from minus infinity to infinity 1 by 5 raised to mod n into z raised to minus n. Now, given function is f of n is equal to 1 by 5 raised to mod n for all n. Now, using definition of modulus, we will be getting f of n as 1 by 5 raised to n when n is greater equal 0 and 1 by 5 raised to minus n when n is less than 0. Depending upon values of n, we will split the summation as follows. So Z transform of f of n is equal to summation n runs from minus infinity to minus 1, and in that f of n will be 1 by 5 raised to minus n z raised to minus n plus summation n runs from 0 to infinity, and in this interval f of n is 1 by 5 raised to n z raised to minus n. Now put the values of n one by one in both the summations, so that will give us, for the first one it will be z upon 5. So if we put n is equal to minus 1, then it will be minus of minus 1 will be 1, and z raised to minus of minus 1. So z upon 5 plus, if we put n equal to minus 2, it will be z square upon 5 square plus z cube upon 5 cube plus so on. And for the second summation it will be 1 plus 1 upon 5z plus 1 upon 5 square z square plus so on. Both are in geometric progression, in which first one is with the common ratio z upon 5 and the first term z upon 5, whereas the second GP is having first term 1 and the common ratio 1 upon 5z, and therefore the summation will be, for the first one it is first term z upon 5 divided by 1 minus common ratio z upon 5 plus, okay, and this is true for modulus of common ratio z upon 5 strictly less than 1. And for the second one, it is first term 1 upon 1 minus 1 upon 5z, and this is true for uh, modulus of common ratio, that is 1 upon mod of 1 upon 5z strictly less than 1. Simplify this expression, we will be getting it as z upon 5 minus z plus 5z upon 5z minus 1. First one is true for mod z less than 5, and second one is true for mod z greater than 1 upon 5, and hence z transform of the function is, or the sequence is, f of z equal to z upon 5 minus z plus 5z upon 5z minus 1 for 1 by 5 less than mod z less than 5. So this is the region which is called as annulus, which already we have discussed in the theory part. Consider the last example, in which general term of the sequence is f of n is equal to 2 raised to n divided by n factorial for n greater equal 0. Now, by definition of Z transform, we will be getting Z transform of the sequence f of n is equal to summation n runs from 0 to infinity, as we have been given n is greater equal 0. F of n is 2 raised to n divided by n factorial into Z raised to minus n. Now, we will combine 2 raised to n and Z raised to minus n. We can rewrite it as summation n runs from 0 to infinity 1 upon n factorial 2 into z inverse bracket raised to n. Clearly, from the Maclaurin series expansion of the exponential function, we can write down it as e raised to 2z inverse. Rewriting this term, we will be getting z transform of the given function as f of z is equal to e raised to 2 upon z. So, which is the z transform of the given function f of n is equal to 2 raised to n divided by n factorial. So, these are few examples which we have, for which we have obtained their Z transform using the definition of Z transform. I hope you have understood this. In the next lecture, we are going to solve, or we are going to obtain the Z transform using the properties of the Z transform. Thanks for watching this video.